So in this section I'm going to look at some of the theory that applies. So firstly, talk about the antenna, the fields and the shape. Secondly, the jamming concept, basically how it works. And three, signals that are used in the experiment. So I'm going to sketch out some of the fields that you get with the loop antenna. So this is a round loop antenna. It could be any loop, square, whatever, rectangular. And look at the field of the cross-section through a diameter over here. And I'm going to put some guidelines over there. This represents the current wire. Current flow like so. It's coming out here. It's going in there. So this is a representation of the H field. Even though it's an AC field, it is non-radiating, so you could treat it as a static or quasi-static magnetic field. So I'll draw some lines of force representing the H field. They're closed loop circles and something like that through the center. They extend further out. They're all closed loops, which I can't draw very well. They're bunched in near the current wire and diverge out here. So what I'm interested in is not the H field, but the flux density, the B field, and we'll look at it along a plane like there, which represents where the gaming chip would lie. A couple of centimeters above the plane of the antenna, which is here. So we're going to look at YB. BY component is important because that is the normal component to the gaming chip, which contains a spiral antenna. And the voltage is induced, which is proportional to the area and the flux density B, the product of B times A. So look at B. So the B over here in this part is this, like so, and component there, and over the wire basically flat. So BY, here would be 0, and here would be, let's say, negative, here would be positive, and this represents the phase. And now drawing out the magnitude as a graph, distance, and this would be the magnitude of B, and this would be the center, and this is the wire position. You would get up a bit, goes through 0 at the wire position, peaks up below, and then goes out. So what's of interest is this amplitude over here relative to this amplitude over here. So this is the area inside the loop, and this is outside the loop. Outside the loop over here. This amplitude here and this amplitude here. So this amplitude over here is approximately 1/3 of this. Now when reading a chip, it's important to have your flux density level above a threshold so the chip gets read. These are the threshold lines. So what we see here is that chips in this zone could actually be read. Chip lies there, it could read because this outside field, this level over here. Now, when we use a jamming loop, and I'll just clear this and show you another view of this. Here's the read loop. This is the loop of the reader. And beside here is the jammer. And just look at the field plot. Outside the reader it goes down like that. Outside the jammer it goes down like that. The intersection point can be fairly accurately determined because it's the intersection of two sloping curves. And what's happening at the intersection, you want to achieve a jam to signal ratio of some value that you know is effective in jamming the chip. And I'll get into that in a minute. Now in practice on a gaming table, let's take a blackjack table. Viewed from the top, this would be the player betting zone. And let's say there's a side bet. And the effective reading zone for there would be there. So any chip sitting in the side bet would be red. Solution for this: design a small jamming loop which would create a field over there, not affect anything in here, so when you try and read the chip, you can't. So this is a jamming loop applied in a typical blackjack installation. Okay, so now we're going to talk about jamming. Jamming is purposeful interference. So if you look at a communication system that has a transmitter and a bunch of receivers, so let's call the transmitter, that's the reader, the chip reader or interrogator. These would be the chips. And here's a communication channel this way. And there's a bunch of chips, let's say, that we want to talk to. And they're communicating back and forth. And it's the medium is 13.56 megahertz, and the carrier is always on. So looking at this as a transmit. And this part is the receive part. Now, if we wanted to prevent communication, we're going to pick the weakest part of the system. The weakest part of the system is the chip. And that's going to be the victim. And we're going to attack the input channel of this chip by applying or superimposing a signal on its normal receive signal that's going to somehow interrupt or interfere with it. And that's what we call the jamming signal. Same signal is, to some extent, is seen by another chip, but it is weaker. So we want to have a strong signal, jamming signal on the chip we want to jam. Not so bad, not so strong in the chip we don't want to jam. And the concept is to prevent the chip from responding. So if we look at time, let's look at some data. So we're going to have the transmitter is sending a bunch of commands in a command word, and it's going down to the chips. The chips, if it decodes that signal properly, is going to send a response back that the reader is going to interpret. So we want to stop this one here. So we have this period of time in here to attempt to interfere with communication. Now, in the simplest systems, they're not synchronous, so we don't have to know that this thing is there and when it actually is. So we're going to just apply some jamming signal indiscriminately in the background and try to affect the chip and not affect the reader. So we just want to affect this guy. Now, what are these signals? The signal level required for jamming has to have a jam to signal ratio equal to or better than minus 12 dB. This is theory. In practice, about minus 10 dB. Now we have a concern with not exceeding the EMC requirements for radiated emission, where we have an emission mask that we have to stay within that's quite severe, because the central region is only for the carrier. It's plus or minus 7 kilohertz. Here you're allowed to have a large signal, but down here off in the shoulders, not really. So this restricts us in the kind of signal and modulation that we're going to use. So we look again at what we need, and this is our decrease of the B field from the reader. We have to hit some number at this point or to maintain our jam to signal. We have to look at what happens and what value we need relative to from here to here and set the jammer level so we do get effective jamming. Now, of course, we're going to modulate the jammer because we just cannot use CW or even ASK. ASK is out of the question. The resulting modulation of use is QPSK. QPSK has got a PSD. I can't draw this exactly, but it looks like that basically. And the first maximum over here is down about minus 13.5 dB from the carrier position over here. So with careful selection, QPSK modulation is going to help on the jamming signal. There's another interesting, useful fact as well, that the reader issues commands at a certain rate. If you can synchronize to it, and that's a command, another command, its rate could be, let's say, every 3 milliseconds maybe, and you only have to apply your jamming for 250 microseconds. So on the fastest readers, which are going quicker than the 3 millisecond command rate, you may end up with a duty cycle of 1/4 if you can sync. This is of help. That's our duty cycle. And the last but important factor is a very small loop antenna is not an efficient radiator. Its radiation resistance is quite high. It's electrically small, so it's nowhere near the 1/10th lambda consideration. It's much smaller than that. So even on a gaming table, if you have a lot of loops and they happen to be active maybe all at the same time, the radiated power very low. So chances are we're going to be within this radiated emission restriction, which never has been a problem even when we were developing jamming equipment for 15693, and the jammer signals were quite a bit higher.